Okay, so let's finish up this question 5. So we had just found the derivative and we are plugging in 2. So, okay, so we need f of 2, which we already know is 6, and then 2 times the derivative at 2. Now remember, this graph is the derivative, so if I go over to 2, I get -1. So I end up with 6 minus 2, which is 4. Now I'm going to use that to write the equation of my line. You can write it in point slope form. So y minus 12 equals my slope times x minus 2. You could go ahead and write it with the y value on the other side. It's up to you. Either one is fine. Also, no calculator. They give us a function. We've got a k value that's a constant. We're only using x values greater than 0. And they first want us to find the derivative. So again, they usually start us pretty easy. So here we go. So on this one, I want the derivative. So let's start with the derivative of f. So the derivative here, well, this is really like k times x to the 1/2, right? So I really have the 1/2 coming out front. My x would go down by a power. And then the derivative of ln x is 1 over x. So if I simplify that a little bit, I get k over 2 times x to the 1/2 minus 1 over x. Okay, for my second derivative, it might be easy just to use this version. So I'd multiply by -1/2. That'd give me negative k, or 1 over 4. And then I'd take it down by a power, -3/2. This guy ends up being plus 1 over x squared. You can do that by hand. And so there are my first and second derivatives. So you can leave them however you want. They'll accept both answers. For part B, they want me to find out what value of the constant k does f have a critical point at x equals 1. Critical point is typically when your derivative is 0. Remember, that's one of the ones. It could also be undefined, but that's kind of what we're looking at. And so we're saying at 1, if there's a critical point at 1, what would that k value have to be to make it to have a critical point at 1? So that's where we're headed. Okay, and then we're going to figure out if it's a max or a min or neither. So I'm going to take my first derivative, and I know that it has to happen when x is 1. So normally I would just set this equal to 0, but because I'm actually solving for k, I can go ahead and set and plug in x equals 1 and the fact that it has to be equal to 0. So that's what I'm doing. So I'm going to use this version. 2 over x, or k over 2, x to the 1/2 minus 1 over x equals 0. Again, I'm going to replace the x's with 1s. So that gives me this. So then I end up with 2. Okay, so now that I know that k is 2, I need to know if that's a max or a min or neither. So I think one of the easiest things to do then is to plug the value back into the second derivative and see if it's concave up or down. So that's what I did. So if I plug in, I'm going to plug in the 2 for k because now I know that that's true. So if I plug in a 2 here, I hope everyone sees this is really -1/2. So I have -1/2 x to the -3/2 plus 1 over x to the second. So I'm going to plug in x equals 1 to test to see if it's concave up or concave down. So when I plug in a 1 here, I end up with -1/2. When I plug in a 1 here, I end up with 1. Because this answer ends up being a positive number, I know it's concave up, which means concave up would make this a minimum. All right, for part C, I want for a certain value of k, the graph has a point of inflection. Find the value of k. Well, point of inflection would mean that the second derivative is equal to 0. So that's what I'm going to do. I'm going to find where I have a point of inflection. And this is important. The point of inflection is on the x-axis. Well, if it's on the x-axis, that means that I know that this point has to be of the form something comma 0. So I can go back up to this equation, I could plug in 0, and I could figure out what must be true. So, okay. So if I wanted to, I can start with that, or I can start with the point of inflection. I'm going to start with this. So I'm going to figure out what would make my point be on the x-axis. So I'm going to set the original equation equal to 0 because I want to know, because I know that that has to be true. So what I know is that k root x equals ln of x. The only problem, of course, is that I have too many variables here. So I went ahead and just solved for k. I also know there's a point of inflection for a certain k. So a point of inflection would be setting the second derivative equal to 0. So I'm going to do that. So if I set my second derivative equal to 0, I'm going to do a little cleaning up here. I'm going to make it x to the 3 halves on the bottom plus 1 over x squared. So if I wanted to solve this, I could move this guy to the other side. I'm going to set this equal to 0. I can move this guy to the other side. And then I'm going to multiply, cross multiply. So I'm going to treat this negative as actually being on the bottom. It'll be easier. So this times this gives me a positive k x squared equals 4x to the 3 halves. I'm going to divide both sides by x squared to reduce. It's not going to completely cancel, so it's okay to do. Here I end up with 4 over x to the 1 half, or root x, if you will. And so now this is why I can solve this. This one is a little tricky. Now that you know that these are both equal to k, you can set them equal to each other. So I can set 4 over root x equal to ln x over root x. Obviously, the bottoms are already equal, so all I need to do is set the top equal. I can take both sides to the e, or the e power of both sides, and I end up with x equals e to the fourth. Now, this is where I almost made a mistake, because this is what I originally had thought my answer was, but then I realized they want the k value. So I actually have to plug that back in to one of these to get the k. It's probably easier just to plug it in here. So 4 over root of e to the fourth, which is actually 4 over e squared. So that was the final answer. That was tricky, but that's why it's a part C. Okay, we have a couple more to go. Question 7 gives you, let's see, it gives you g of 1 is 2. You can only have x values that are bigger than 0. Gives you the derivative and the second derivative. That's great. It is also a calculator question. So the first one said find all values of x in the interval from here to here, at which the graph is a horizontal tan. Well, again, a horizontal tan is when the derivative is equal to 0. So I could just graph the derivative and set it equal to 0. And I think on this one, I think this is a typo because I'm pretty sure this is supposed to say g. Okay, so I'm looking for when, g is 0. So I went ahead and graphed this, and I graphed the derivative, and I looked for when it was a 0, and I got that it was a 0 twice. It was actually a 0 at 0.163 and at 0.359. So I had 2 places. On what subintervals from that little interval, if any, is it concave down? So concave down, remember, is when you're looking for when the second derivative is a negative number. So I graphed the second derivative and looked for when my second derivative was less than 0. And it was less than 0 from 0.129. I had to find that 0 up to 0.22. I also had to find that 0. So again, I actually defined when it was zeros. These were the zeros, and then this is when it dipped into the negatives. For part C, you don't need to worry about part C, and you don't need to worry about part D. We'll deal with those when we do unit 4, so you can skip those for now. All right, question 8. First of all, it's no calculator. It tells you it's twice differentiable, which means you know it's continuous for f and g. They give you various values of f and g, regular and prime. So part A says find the x coordinate of each relative minimum on f. So I'm looking at minimums for f. Well, first of all, if you're looking for maxes or mins, you know you're going to start with when the derivative is 0. So that's something I'm going to start looking at from -2 to 3. So when is my derivative 0? It's 0 here and here. But just because it's 0 doesn't mean it was a max versus a min or back and forth. So how do I know? Well, to be a minimum, remember, you needed to be decreasing and then increasing, or have a negative slope and then a positive slope. So I need to have a negative value switching to a positive. The only time I have that is right here. So the only place I have a minimum would be at x equals 1. And your justification could be to show that it has a negative slope or is decreasing on right beforehand and increasing right afterwards. Part B says explain why there must be a value of c from -1 to 1 such that the second derivative is 0. one is interesting, and you kind of have to think about it graphically, guys. So if you think about what the graph of the derivative would look like right here between -1 and 1, you have zeros at -1 and 1 for the derivative, and then it's negative. Well, if it's negative and comes back up and hits the 0, there must have been a place somewhere in between where it had a minimum. And so that means there must be a place where the second derivative is 0. Because remember, mins and maxes of the first derivative are zeros of the second derivative, or mins of those. Okay, for C, the function h is defined by this. Find h prime of 3 and show your computations that lead there. Okay, so, well, first of all, I need to find h prime of x. So I have composition. This is a chain rule, guys, remember? So I have to start on the outside. So the derivative of ln is 1 over what's inside, and then times the derivative of what's inside. Okay, so then I'm going to find h prime of 3. So I'm going to rewrite it, 1 over f of 3 times f prime of 3. And then I'm going to use my table. 1 over f of 3 is 7, times f prime of 3 is 1/2. And so my final answer is 1/14. I hope this was helpful, and good luck.